Hi, everyone. Welcome to the 51st session of the MedAI group exchange sessions. This week, we have Andrew Ilyas from MIT here with us to present his work on data models, or AKA how to predict predictions from training data. Andrew is currently a fourth-year PhD student at MIT, and he's co-advised by Aleksander Madry and Konstantinos Dasalakis. I'm sure I'm butchering the name, but hopefully it's okay. His research focuses on robust and reliable machine learning with an emphasis on the ways in which often unintended correlations present in training data can manifest at test time. He's supported by an open philanthropy project AI Fellowship. And thanks so much, Andrew, for joining us today. And I guess before we start, do you have any preferences on how you'd like to take questions? Are interruptions okay, or would you like them at the end?
Yeah, for sure. Thanks for the introduction. Questions at any time are super welcome. Feel free to just jump in. I don't have enough, I have relatively few slides, so I can spend long amounts of time on a single slide, even if that's better.
Awesome, okay. Yeah, so maybe then we can make this as interactive as possible. And without further ado, let me hand it over to Andrew.
Great. Yeah, thanks so much for the introduction. And yeah, as I said before, feel free to interrupt really at any time. So the paper I'm presenting, as Nanti has said, is data models predicting predictions with training data. And this is joint work with my collaborators at MIT, Sam Park, Logan Engstrom, Guillaume Leclerc, and Aleksander Madry, our advisor. Okay, so our starting point with this project was basically thinking about what we might call like the anatomy of an ML prediction. So if we think about a specific machine learning prediction, like I might have this image of a dog if I'm doing image classification. I might have this test input of a dog that I feed into a machine learning model, and then the machine learning model tells me that it's a dog with like 85% confidence. And intuitively, I sort of know that this dog prediction is a function of both the training data that I used to train the model and the learning algorithm that I applied to this training data. And these two things together are what gave me the model output of like dog with 85% confidence. So our driving question throughout this project was whether we could get a better understanding of how exactly the training set and the learning algorithm combine to give us this model output. And if it wasn't clear from, I guess, the title of the talk, our proposed approach to this is a framework that we call data models. And so for the next couple of slides, I'm going to introduce what the framework is and how it works. And then I'll move into some applications that we're kind of excited about. Okay, so before I actually introduce what data modeling is or what data models are, I want to define a function that's going to come up a lot throughout this presentation, something we're going to call the model output function. And so I'll use f to denote this model output function, and f is going to take two arguments. The first is going to be a specific test input. So for example, this image of a dog. And we'll call that x. And the second argument is going to be a subset of some larger training data set. So for example, I might have some set S in context, like the ImageNet training set, and then S prime, which is the argument to this function, is any subset of that training set. And the reason why it's a subset will become clear very soon. The output of this function is what will happen if I train a model end-to-end on the subset S prime, and then evaluate on X. And this evaluation is just in terms of any loss functions. We use margin in our paper.
Quick question, Andrew. So yeah. X here, it's not part of the training set. It's a completely new input, or
yes, it could be part of the training set, but like it's an arbitrary input. It's not necessarily part of the training set.
Sounds good. Okay.
Yeah, it's easier to think about it if you think of it as just like a test example.
Got it. Thanks.
The important thing is that it's one specific image or one specific input. Okay, so if we think about it, this function, like f of x comma s prime, is sort of exactly what we're interested in understanding better. It's exactly what we're interested in analyzing, because it maps from the training data that you train on to the model output. And so that's exactly the pipeline we want to understand. So we want to study f. The problem, though, is that f can be pretty complex. Like f can be, randomly initializing a neural network, training with a bunch of steps of gradient descent, and then evaluating this loss function. There's no real clear way to analyze that. So the idea behind data modeling is rather than study f, we're going to try to design some surrogate function, f hat, that's going to approximate F as closely as we can, but be also very easy to analyze on its own. And the idea is that if we can do this, then we can use insights that we get from F hat to better understand F. And the important thing here is that F hat operates on subsets of the training set. Like F hat is a map from data to predictions. Okay. So a natural question is like, okay, how are we actually going to do this? Like, it would be great, sure, if we had an F hat that like magically approximated training a neural network end to end, but like, what are we actually going to do? So what we're going to do is, for now, we'll just fix a specific target example X. So for example, this might be the image of the dog that I showed earlier. We won't think about varying X. Once we fix the specific target example X, our problem actually becomes a supervised learning problem. And what I mean by this is that I can sample a random subset of the data set. I can train a model on that subset, and then I can collect the output on X. So here I've collected this pair. The pair is S1, which is this random subset, and the output is F of X comma S1, which is what happens if I train a model on S1 and then I evaluate on X. I can then sample another new subset, S2. I can train on S2. I can evaluate the model that I get on X, and then I can collect another pair. And I can do this over and over and over again until I've collected M random subsets, along with the corresponding model outputs that happen when I train on that subset and evaluate on X. And I'm going to treat these as input-output pairs and fit a parametric model to these input-output pairs. So this is still pretty high level. I haven't exactly said which parametric model I'm going to use or how I'm going to parameterize it, but that's the sort of intuition that's going to be our high-level approach to data modeling.
Sorry, when you said like you're taking the output, which is a functional output, so are you talking about the probability or are you talking about the class levels?
Oh, that's a great question. So the question is, what's the F here?
Mm-hmm.
Yeah, in our paper, we study the margin.
Oh, okay.
But you can think of it as just like a loss function. And there are like some reasons why we pick margin that are talked about in our paper, but it's not really important. Does that answer the question?
Yeah, it's perfect. Yeah,
Okay,
I was just confused, like if you use like margin or probabilistic output. No, I think it's
so it's margin. Great. Yeah, thank you so much for the question. Okay, so having yet said what exactly we're going to do, there's still some design questions that remain unanswered. First, how exactly do we generate the data? It's like, which training subsets do we actually use? I just said we were going to sample random subsets. What does that actually look like? The second design question is, what sort of model are we actually going to fit here? Like what's the G should be F hat, but what's the class of F hats that we're going to be optimizing over? So what exact parameterization are we going to use? The first question is pretty boring, so I'm just going to skip over it and tell you that the way we sample subsets is just by sampling random alpha-sized fractions of the whole training set. So for all intents and purposes, just think of alpha as like a half, and we're sampling like random halves of the training set. The more interesting question is, what sort of model can we fit? And we need this model to be simple to analyze on one hand, but also expressive enough to capture, this process of training a neural network end to end and then evaluating on X. We basically said, let's not worry about the expressive enough thing. Let's just make sure it's really easy to analyze. And so we actually chose a linear model. And we'll see that this linear model actually works surprisingly well. So what I mean by a linear model is we're just going to think of, again, I think F hat is just going to become G now because it's a function of just the set. But anyways, we can think of this function, the surrogate function, as just an inner product of two vectors. The first vector is what's called the indicator vector of the subset. So for any subset S, the indicator vector is just a binary vector that has 1 wherever we included the training example and 0 wherever we didn't. So the size of this vector is just the dimension of the training set. And all the entries are either 1 or 0 based on whether or not that training example is present in the subset. So we take the inner product of that and what we call the data model parameters. So this is going to be a learned parameter that we're going to learn specifically for the test example X that we're thinking about right now. So specifically for that dog, we're going to estimate a single vector that has 1 scalar weight per training example, because it has to be the same size as the indicator vector. And we're going to predict the output of training a model on S prime and then evaluating on X as the inner product of this learned vector and that binary 1, 0 inclusion vector for the subset. Okay, one last question. How do we actually get this learned parameter vector? And so this just involves putting together the last couple of slides. Again, remember what we did is we fixed a specific targeting example X, then we trained a whole bunch of models, and for each model, we collected the subset along with the output of training on that subset and evaluating on X. So after doing this, again, I remember I said we're just going to treat this like a supervised learning problem. And we know how to do supervised learning problems. We just use actually sparse linear regression. And so I'm going to go through and sort of explain each part of this, but this should look very similar to just like standard least squares regression with regularization. So we're going to minimize overall possible weights, average overall.
Sorry to stop you again. So how do you decide the M?
Yeah, that's a great question. I'll probably skip over it, but the idea is we just like kept increasing M until.
So it's more like an experimental variable, right? It's you don't really have any theoretical explanation. Okay.
Yeah, exactly.
Okay.
And in our paper, I don't think I'll have it in this presentation. It might be an extra slide, but we have like how the loss decays as a function of M.
So you did observe like any improvement in loss while you are increasing the M, right?
Yes, we do.
Okay. Okay.
Yeah, a significant one actually.
Okay.
Thank you for the question. Okay, so we're averaging over all the subsets we sampled. On the left-hand side here, this is like the data model prediction for what the margin will be if we train on SI and evaluate on X. So again, just the inner product between the weight and the indicator vector. And then on the right-hand side is what actually happened. It's what this involves training a model on that SI. This is the output that we collected. Training a model on the SI and evaluating on X. And then the last thing is just regularization that helps both sparsity, which helps with interpretability, and improves our generalization a lot. Yeah, if this didn't make sense, you can feel free to, like, I'm happy to spend a while on this slide.
I had a quick question, more of a thought question, like why is sparsity on theta like actually important for you, or why did you choose sparse regression at this point?
That's a great question. A couple of reasons. The first is that the first is sort of experimentally driven, and we just like found that it helped generalization more than doing unregularized regression, probably just due to like model misspecification and stuff. The second thing is that actually the sparsity helps a lot in like downstream applications. So like we're going to talk about, for example, interpreting these vectors as like weights in a graph, and like the fact that they're sparse means the graph isn't fully connected. But we can talk about it. I'll revisit it later.
So if I understand correctly, so your indicator vector itself is going to have, let's say if your M is, like if you're training, if your alpha value is 0.5, then your indicator vector is roughly going to have 50% ones and 50% zeros.
Yes.
And the weights, you are making them even. So are you trying to induce sparsity on the ones that actually contribute, like the 50% of the ones that contribute, or are you like?
So the sparsity is over the whole weight vector in general. Basically, what sparsity corresponds to in this case is that you're essentially hypothesizing that, for example, for neural networks, getting a single training example right isn't really a function of like having all of the training data. Like if I'm looking at a specific cat, for example, it doesn't really matter. Like the effect of like some totally unrelated image is probably about 0. And so I'm better off just like setting it to 0 than trying to estimate this like really, really tiny quantity.
I see.
Because I'll probably estimate it wrong. And the way that we the way that we get the sparsity level, so the way that we set this regularization parameter lambda is actually just via cross validation. So it's whatever helps us get the best generalization. So we have some like held out set of pairs, and then we like do a sweep for lambda and pick the lambda that helps us best predict out of sample.
I see. I guess I'm also wondering if like adding an L2 regularization will aid, or did it actually, can it hurt?
It could help. We haven't tried it.
I see.
But it might help. Yeah.
Got it. Thank you.
Thanks for the question.
Let's like just continuation for because you mentioned sparsity, but don't you think like that will also be affected by which sample you chose? Because if the sample is very close to boundary, like the X, I mean,
Yes.
if the sample is very close to boundary versus like if the sample is completely negative, or if the sample is in the positive category, that may also have some effect based on the model
Yes, for
performance.
sure. Yeah, so the lambda is actually set differently for each X. Like this is just for a single X. And for each X, we sweep over a bunch of possible lambdas from like the like we like pick the lambda that would make the weight vector all 0, and then we do a sweep from that lambda all the way to 0. And we pick the lambda that'll let us best predict how
for
we're
that
going to do on
particular
that
S. Okay.
Exactly.
Okay, got
yeah.
it.
Yeah. Another great question. Cool. I'll pause for a few more seconds just in case there are other questions. Amazing. Okay. So hopefully at this point I've said enough so that to explain like how we actually get these theta, but I haven't convinced anyone that like this thing actually works. Like I showed you that we can estimate parameters that try to predict model performance, but how do I convince you that like we actually do predict model performance? And so, actually, before I get to that, I just want to provide first a quick summary of the last couple of slides. So what does our algorithm look like from start to finish? Okay, so here I'm going to set M to 500,000. So 500,000 times, I'm going to pick a random alpha fraction of, let's say, CFAR 10. I'm going to pick a random alpha fraction of the training set. I'm going to train a model. In our paper, we use ResNet 9s on this subset. Then I'm going to measure the margin on every single test image. And for each test image, as we were saying before, we're going to record the pair characteristic or indicator vector of the subset and the whole vector of margins on the entire test set. Then once we've collected 500,000 of these pairs, for each test image, we're going to fit a linear model, a separate linear model with its own regularization constant from the indicator vectors to the margins. So just a note about this 500,000. Setting M equals 500,000 means that we have to train 500,000 CFAR 10 models, which we thought would be really hard. And so we actually developed our own training library that's publicly released that let us get the training time for these models down to basically, I think amortized, it's about 2 seconds per model on a single GPU. To get to like 92% accuracy. And so if model training is a struggle, I would recommend at least taking a look at the library. But yeah, we managed to get 500,000 of these CFAR models and get these data models for every single test image. So at this point, what we have is for each test image in the CFAR 10 test set, we have a vector, and the vector of size is of size 50,000, where 50,000 is the size of the train set, and each of these vectors is trained to predict model outputs for its corresponding test example. So if there are no questions, I'm going to keep going into how do we actually evaluate if these things work at all. Okay, great. So we have these 10,000 vectors. They're each of size 50,000. How do I know they work? Well, one very natural measure.
Actually, Andrew, sorry, I just wanted a clarifying question about the previous slide. So if I understood it correctly, so for every test image, now you're going to have a 10,000 like outputs from your data models, or am I missing something?
No, for each, so there are 10,000 test images.
Okay.
For each of these test images, we have 500,000 random subsets and 500,000 outputs from each subset.
I see. Okay, so for a given test image, you have 500,000 outputs, and then you have 10,000 such test images.
Exactly. Yeah. And so we're basically we need to do 10,000 linear regressions separately.
I see. Okay.
And so, like, after we do those 10,000 regressions, we collect the weights, and the weights are of dimension 50,000.
Got it. Sounds good. Thanks.
For sure. Okay. Okay, so if there are no more questions, I'll go to the next slide. but you can feel free to interrupt me if I've said anything confusing. Okay, so at this point we have a bunch of these vectors. How do we know that we actually did anything useful? So again, remember our two goals were to have something that was easy to work with. Linear models are pretty easy to work with, but also to have something that actually approximates this like model output function that we care about approximating. So one really natural way in which we can measure how well we're doing is to look at basically out of sample performance. So if we sample a bunch of new subsets that we've never sampled before, and then we train models on them, and we record what the outputs are, if our data models work well, then we should expect to be able to predict what's going to happen when we train on these subsets that we've never seen before. And so what I'm going to show you next is a graph that's aggregated over a bunch of different target examples. Each of these target examples has their own data model, again, that we estimated on the last slide, and aggregated over a bunch of random subsets that we've never sampled before. Okay, on the x-axis, I'm going to put what we predict the margin is going to be when we sample on a given subset Si. And on the y-axis, I'm going to put what the expected actual margin is. And the reason we need the expected value here is that neural network training is non-deterministic, and so we actually need to train like a bunch of these and average them for each subset, just so that we reduce the variance in the y-axis. Okay, so just to be clear, this is going to be a scatter plot. Each dot in the scatter plot is going to correspond to one target example and one subset. And then the x-axis is going to be what we predict is going to happen, and the y-axis is going to be what actually happened. Okay, and this is what the scatter plot looks like. And so this is actually pretty close to what we would hope for ideally, because it's very similar to the line y equals x. And what this is saying is that generally when we predict that the margin is going to be high, the margin is high, and when we predict the margin is going to be low, the margin is low. And I've sort of zoomed in on a specific part of this graph where we like stop aggregate. So like the big blue line is aggregated over both target examples and subsets. And then the zoomed in part of the graph, I've colored each specific target example a different color just so that we can see that like, it's not just an aggregate. Actually, for a specific target example and just varying over subsets, I can predict, data models can predict what's going to happen if we train on a given subset and evaluate. And so the result here is that data models can actually successfully predict end-to-end training, despite the fact that we're just using a linear model to predict this like super long and convoluted process of training a neural network. And so one open question that we don't really think about in our paper is like, why should we expect this to happen at all? Like this like should not look like like we would not have predicted that this would look like the y equals x line. And so it's sort of an interesting theoretical question to ask, like, why would this actually happen? But we're going to ignore that and just be really thankful that it does happen, because it means that we can analyze neural network training by just looking at this linear model. Okay. So in our paper, we do a bunch of other validation, but I'm going to skip over that and just talk about how to actually apply these things. And so what we have right now is this kind of magical approximation that lets us approximate training a neural network end-to-end on a subset S prime using a simple inner product. So how do we actually use this? In our paper, we have more applications than I've actually listed on this slide, and I won't be able to talk about all the applications I list on this slide. So if you're interested in any of them specifically, I'm happy to talk offline. But I'm going to talk about analyzing model brittleness with data models, predicting what we call data counterfactuals. I'm going to skip over a couple of applications of finding train test leakage. And then I'm also going to talk about how to use data models as an embedding, which is something we're really, really excited about. And so I'm going to focus on just 3 of these applications: brittleness, counterfactuals, and embeddings. Okay, I want to start with brittleness because it's kind of the most natural sort of application of data models. And when we say brittleness, what we mean is what is the smallest set of examples that I can remove from the training set to cause a network to misclassify a given image. So I might have an image, for example, that's classified correctly and classified consistently, but I want to know, like, if I slightly change the training set, is it still going to be classified correctly? So here I have an example of like this plane that's correctly classified, and then I remove a couple of examples, I train, and then, sorry, something happened to my slides, but okay. I train and then I classify incorrectly. So ideally, we'd like to find this like minimal subset of images that would cause me to misclassify an image correctly, because that's like a very natural notion of brittleness to try to quantify. The problem is that if I try to just like brute force search over the entire training set, it's going to take me forever. There's no way I can possibly do it. And even if I try to like randomly sample subsets, I'm also never going to find it. It would take like, you'd have to train not just 500,000 models, you have to train like tens of millions of models to find these subsets. Okay, so we have exponentially many subsets to try, but the nice thing is that we have this approximation that lets us skip over the step of training a neural network and just plug it into this linear model that we have instead. And so what we propose doing is still do this like search over subsets that takes exponential time, but instead of actually training the model each time, just plug the subset that we're considering into the data model and use the data model to guide the search. And so the results of this are here. On the x-axis of this graph, I have the number. So for example, for now, just like look at only the blue line. I'll explain the orange line a little later. But on the x-axis of this graph, I have the number of training examples that we need to flip a test image's prediction. So this is a CDF over the entire test set. For each test set image, we do this process that I described in the last slide, where we use data models to do a guided search. We use data models to do a guided search for the smallest possible subset that would cause me to misclassify the image. And then we actually test this out. We verify that this subset does actually make me misclassify the image. We do this for every single test example. And for each test example, we get a brittleness score, which is what's the minimum number of examples I need to remove. Then this graph is just a CDF over that brittleness score. So what this graph tells you is that for 20% of the training set, for 25% of the test set, we can actually remove just 100 images or just 150 images and misclassify those examples. And the important thing though is that these 150 images are specific to that test example. Like it's not 150 images that would make you lose 25% of your test accuracy. It's that for each of those images, if you search for the worst case 150 images to remove, you will misclassify those images.
Quick question here. So
yeah.
Did you find in your analysis that the 0.2% training examples that corresponded to a particular test example were either like semantically similar or belong to the same class? Like, is there any insight on?
Yes. Yeah, I'm actually going to talk about that just the next slide.
Oh, okay.
So I'll defer that question to one slide for now.
Sounds good.
So that's what the blue line is. The orange line is if we take the same test examples that we identified with the blue line, and instead of just removing those examples, we actually mislabel them, the classification is even more brittle. So like with 200, like relabeling 200 examples per test example, we can actually flip the classification of any test image in the test set. Or with like just relabeling 50 examples, we can remove like half the test set. We can flip the classification of like half the test set. So in the relabeling sense, the classifier is actually extremely brittle. But the removing sense, it's still pretty brittle, but it's a little less brittle. Okay, so now to tackle an example of what these things actually look like. So here's a representative example that we really like. So this is a boat. It's classified with 71% confidence correctly. And it's classified, I don't have this on the slide, but if you like retrain the model a bunch of times and you count the percentage of the time it's correct, the model is correct on this boat 85% of the time. So you would think that like the model is actually reasonably confident in this prediction here. And it turns out that removing these 9 images from the training set and retraining a model on the remaining like 49,991 images will make this boat consistently classify as an airplane. And so if we sort of visually inspect these images, we see that what we're actually kind of doing is removing all of the instances of boats on grass. And the remaining things that like look white and are on grass in the training set happen to be planes. And so the model, like we might hypothesize that the model is now associating this like white thing on grass as a plane. And so this brittle example isn't brittle on the original training set, like is consistently classified on the original training set because there are a bunch of very similar training examples. But if we remove those very few similar training examples, the model really isn't sure what to do. So hopefully that answered your question about the semantic similarity stuff. And in general, the trend is that like you basically always want to remove stuff that are similar. Like removing things that are different is kind of useless. Okay. So now I'd like to argue that what we just saw, this like model brittleness, is just one specific instance of a more broader thing that we might call data counterfactuals. And what I mean by data counterfactuals, we're kind of broadly interested in this question of, if I remove some arbitrary set of images from my train set and I retrain, what is my classifier going to do? And we sort of call those class of questions data counterfactual questions. And the reason it's not obvious we can do this from what I've shown you already is that if we think about like that y equals x plot from a while ago when we were evaluating data models, all of those subsets were randomly chosen from the same distribution of subsets that we actually used to estimate the data model. So all of those subsets were like random halves of the training set. And now what I'm asking is, instead, let's say I don't care about random halves, let's say I'm very specific and particular about how I pick those training sets S. Can my data model still predict what's going to happen if I train on arbitrary subsets of the training set? And so this is a much more powerful capability than what we even trained the data models to do. And this is the same style plot as before, but now each color represents a different way of removing inputs. So we might remove like the top weights, the bottom weights, the most similar images according to like SSIM. They all represent different ways of picking this counterfactual train set. And what we find is that even though it's not the perfect y equals x line as before, the correlation between what the data model predicts and what the actual counterfactual is still like a super strong correlation. And so what this implies is that data models are still useful at predicting what's going to happen when we train on arbitrary subsets, despite these subsets being outside of the distribution that we actually trained the data models
on. Another quick question here.
Yeah.
So sure. Do any of the scenarios that you listed include like just removing one class completely? Because I would assume that might be hard for the linear models to, like, let's say you have 10 classes and then you just completely remove maybe one or two, and then how is the model ever going to know it's?
That's a great question. I'm not actually sure. I'm not sure we got that far. I'm not sure we tried that many. I think this goes up to removing 3,600 examples, which still would not be enough to remove one whole class, because that would be 5,000 examples.
I see.
So I can try that and get back to you, but this is up to removing 3,600 examples.
I see. Gotcha.
But like one of the lines is actually removing all the examples from the same class. It's just that we don't remove the entire class.
I see. Okay.
We remove like most of the class.
You'll be able to identify data points that are actually harmful for the model performance using this method?
Yeah, that's a great question. Actually, in this paper, we didn't look at that, but there's a recently released paper, I'm not on it, but from our lab, about using data models to remove, they basically improved the performance of transfer learning by removing a bunch of harmful examples from the pre-training task and improving accuracy on the downstream task. And I think that just came out like yesterday or the day before. So I actually haven't gotten the chance to read it thoroughly, but I know that's what they do.
Yes. Thanks.
One interesting thing that's very related to that question is that if we just look at on-distribution performance, for CFAR10, we weren't actually able to find any training points that were overall harmful for test accuracy. Like there are training points that are harmful for specific subpopulations, but usually those training points were also helpful for other subpopulations. And so there were no real training points that were like overall beneficial to remove. And that's probably just because like the label noise in CFAR10 is pretty low. And so there are no like very overtly, or not no, but there are very few very overtly mislabeled examples. So the story might change. The story does change, for example, if you look at transfer learning or if you look at ImageNet, which is what we're working on next. Okay, Great. So that's the data counterfactual application, and I think I have about 10 minutes. I have 8 minutes left. Okay, that should be plenty. So the last application that I want to talk about is how to use data models as an embedding. And this is something we're particularly excited about and have some follow-up work coming out soon that I'm happy to talk about after too. So what do I mean by this? What I mean by using data models as an embedding is rather than treat theta as just like the weights of some linear regression, we can think of theta as embedding this test example into the space like R 50,000. So we can think of like this test image of an airplane. Its weight vector has one coordinate per training example and sort of encodes the dependence of this test example on each, the dependence of this test example on each training input. And it turns out that this embedding has like a really nice, well-behaved structure. And so a few properties that I want to point out even before I show any applications are this embedding means the same thing across different model architectures, across different loss functions. So like unlike the embedding space that might come from just like using the last layer of a neural network, here like the coordinates mean the same thing regardless of what you're doing. Like the first coordinate is always your dependence on the first training example, which makes this sort of uniquely useful for like combining different models or doing a variety of applications. Okay. And I already said this, but basically the coordinates of this embedding are just how predictive of X is each training example in the training set. Okay, so what can I do with this embedding? Well, one natural thing to do with embeddings is use them to define a similarity measure. And so for two test examples, X1 and X2, I can define their similarity as just the inner product between their, what we'll call data model representations. So I can take the weight for one, I can take the weight for the other, and then I can come up with a similarity metric that basically asks how similarly do these things depend on the training set? Like, do I use the same training examples to make decisions on X1 and X2? And after I've done this, I can use the similarity metric to sort of write down a graph over my whole data set where the edges are exactly the similarity between the two test images. And the nodes are the test images themselves. And it turns out that the clusters in this graph, as one might expect, correspond to like images with very, very similar features. So for example, we found clusters that correspond to like planes on sunset backgrounds, clusters that correspond to like deer on golden grass backgrounds. And then the negative edges in this graph are actually sort of subpopulations that are almost fighting one another in the sense of doing better on these deer. Like the training images that help me classify these deer correctly actually hurt me when it comes to classifying these planes. And the reason is like somewhere in the training set, there are a bunch of deer on golden backgrounds. And those deer on golden backgrounds make me associate golden backgrounds with deer, which helps me classify deer, but also hurt when it comes to classifying airplanes on golden backgrounds, because now I've associated golden backgrounds with deer. So I'm happy to repeat that, but the main idea here is that positive edges correspond to test images that depend on the same set of training examples in the same way. And negative edges correspond to test examples that depend on the training set in opposing ways. And we can make this even more concrete later. And the cool thing about this that we're still looking into is that it'll enable us to use a whole host of like algorithms from graph theory and like graph mining and stuff like that to actually understand data sets better. And so I want to show, I have enough time to show two applications of this graph view that are sort of exciting. So the first thing that I was talking about before is we can just do clustering over this graph. We just apply like a standard clustering algorithm, and what we get are these like pretty semantically meaningful clusters. So for example, here are 5 example clusters from boats that are all, you can sort of see that they have feature in common, whether it's being diagonal or being red or being steamboats, or there's sort of one unifying feature of each cluster. Some of the clusters, so for example, if you look at like the 3rd row of this horse cluster, it's actually like a bunch of images from the same horse show or something. And so they're all put in one cluster together. So that's spectral clustering, and you can sort of think of this as like a data-driven way of finding subpopulations that are actually algorithm relevant. Like we sort of know that these subpopulations are intimately tied to the way that the model class is classifying, and they're not just like visually nice. And there's like a mathematical way to think about it that I don't want to put on the slides, but I'm happy to talk about after as well. The second application that I want to talk about from this graph theory perspective is what if we just take the adjacency matrix that I talked about a few slides ago and we run SVD, which is like a standard tool for like finding important communities in a graph. And what we recover is exactly this phenomenon that I was talking about earlier. So if we run PCA on this adjacency matrix, we basically find these principal components, or like singular vectors, that correspond to images in the training set that affect the test set in opposing ways. So I'll just go through these three examples as an illustrative example. So the first row here sort of tells us there's some group of images in the training set, which we can hypothesize are going to be red cars. And that group of images helps me classify the images on the left, the test images on the left, but hurts when it comes to classifying the test images on the right. And so I can think of those training images that I don't visualize here. We can think of those training images as being red cars, and training on those red cars makes me think red things are cars. So I do better on the left side images, but it also makes me think red things are less likely to be trucks, which makes me do worse on the right side images. And you can sort of repeat the same intuition for this plane example where like white thing on blue background is either bird or plane. And including or removing some set of training examples makes me more or less likely to think that they're a plane. And the same for like this like horse versus dog on a green background in the same position. And so we can sort of think of these as like almost dueling subpopulations. And so it's sort of related to C's question from earlier about whether there are overall harmful examples. And I guess the point that this sort of drives home is like for each example that you might think is harmful because it's hurting your classification on like, for example, this set of horses, there's some other opposing subpopulation that has the same feature with a different class that you're actually helping. And again, yeah, sort of the same intuition as the clustering thing. Cool. So with the remaining time, I want to go through a couple of takeaways and then maybe open up to whatever questions people have. So what I hope I've done in this talk is introduce data models as a framework for understanding both data and machine learning predictions. And the core idea here was to sort of first define this model output function and then learn a data to output mapping that's simple using a supervised learning framework. It turned out that for neural networks, at least, just a simple linear instantiation of the supervised learning framework worked really well and gave us a versatile tool for understanding both models and data. Models in the sense of predicting counterfactuals and finding brittleness, and data in the sense of this rich embedding that let us explore our data set a little better. There are a bunch more applications in the paper, as well as some more motivation, and then there's also a series of blog posts that's still ongoing that might have a little more detail. Yeah, that's it. Thank you.
Awesome. Thanks so much, Andrew. I guess before we open the floor up for questions, maybe we can give a round of virtual applause for the great talk. Yeah, feel free to ask your questions now. I can actually get started with one. So I was, did you do any experiments to see what fraction of the training set is actually important for training like your data models? Like if you choose your alpha to be very small, does it actually make it harder to, find a robust set of weights?
That's a great question. And we actually have like, we struggled with this question a lot, and we actually have like 2 or 3 appendices all about how to pick alpha. And the intuition we sort of settled on is it depends on what sort of dependencies we're interested in surfacing. Mm-hmm. So you can sort of think as alpha goes to 1, we're doing something very close to like leave one out, like influence estimation, basically, where we leave each training example out and we see what happens. So this is going to be very good at detecting sort of local features. like if we have like a duplicate image or a very uncommon feature where like removing one image will drastically change stuff, setting alpha very close to 1 helps a lot with that. But if we're interested in sort of detecting these very general features like blue skies, if I remove like one blue sky image from the training set, I'm probably not going to do any worse on other images that have blue sky. And so as we set alpha closer and closer to 0, we miss out on a lot of these like very near, we miss out on a lot of precision in the weights, like you were saying, but we also are able to capture much larger subpopulations. So we can find things like all the images with blue sky, even though it's a very large subpopulation. And so we have a bunch of like simulations of like simple linear regression settings and things like that in the paper that sort of help make this intuition a little more concrete. But it's a really great question and something we're still investigating.
And yeah, that was, I think that answered my question really well. But just as a follow-up, more like a thought experiment, because you are doing this training of the data models a priori before you're actually like doing the, like analyzing them for each test sample, would it make sense for you to like set a bunch of different alpha values and just train a bunch of data models and then kind of see, okay, if I have my alpha to be 0.001, I have this kind of thing. And then if I have alpha to be 0.999, I have this kind of dependence, and then kind of get an explainability out of, it's very high level, and probably you might want to put, like, I'm not entirely sure how that would work as well, but I think.
I mean, like, you're spot on in the sense of, like, in our paper, we actually train data models for, I think, 10%, 20%, 50%, and 70%. And part of our analysis is like seeing how our results change as we vary the alpha.
Okay.
So you might want to look at the paper for that. I guess the downside is we don't find like any super concrete trend that we can really pinpoint and be like, here's the exact difference, other than, as you would expect, as you decrease the alpha, which is sort of lines up with the story that I was saying. As you decrease the alpha, your average sparsity that you find decreases. Like your weights get more and more dense, which sort of lines up with this like larger subpopulation story. But beyond that trend, which holds up super robustly, beyond that trend, it's hard to see in the qualitative results how exactly alpha is changing things.
Nice. Okay, thank you.
I think this algorithm would be very helpful for like noisy data sets. Probably like something not much noisier than CVAL10. Have you experimented on that? Say ImageNet or some other data sets?
Yeah, so we're actually in the middle of applying this to ImageNet. The challenge there was training enough ImageNet models. And so we like, that was part of the reason why we actually made this library, is we finally got ImageNet training down to like something like 10 minutes to train on a single GPU, so that we can actually afford to train like thousands of ImageNet models. And so we're actually in the middle of testing out exactly that, of like trying to find images that have consistently negative weight and removing them. But I will say that so far the ImageNet results, I don't have any on hand, but the ImageNet results we have look really cool. In the sense of like, there are some very obvious misclassifications that you can find and like instances of label noise.
So I wonder, do you really have to, so every time when you train an ImageNet model, you basically train from scratch for all the layers, right? Do we really have to do that, or can we just like freeze the previous few layers and then
that's a sorry, that's a really great question. I actually don't know the answer. I know that some people I've talked to are interested in finding like, in general, faster ways to approximate this, because you don't want to like have to train 100,000 models every time you want to switch data sets. So I don't actually know the answer to that, but that line of questioning is like really is a really good one, I think.
Sounds good. Thanks.
Thanks for the question.
Any other questions from anybody else? Okay, I guess if not, oh, sorry, was there one more?
No, I was just like, I wanted to ask you that since you mentioned the rich embedding in the last slide, did you look at the embedding space particularly? Like, because the
Sorry.
examples that you were showing before, there's the image examples, like the planes and the deers.
Yeah.
Do you literally look at, like, when you train different model, how close they are in the embedding space? Or
Yeah. So one upcoming result that I'm really excited about that I didn't get the chance to talk about here is because this embedding space means the same thing for different models. We can actually use data models to do like model comparisons across architectures. So I think like you were saying, like we can look at the embedding space of two different models and ask like, how are these embedding spaces different?
Exactly.
And by comparing the two embedding spaces, we can find like features that one model uses that one model doesn't.
Yeah, I was thinking exactly on that line. Like probably it may help you on also understanding the model interpretability. Like because if you look at the embedding space, like one versus another model using the similar type of linear model that you train, of course you will get some insight of the model learning too.
Yeah, that's totally right. And actually, there hopefully should be a paper on arXiv in the next few weeks that does exactly that.
Okay.
Oh, and just a quick question on the slide that you have here. So when you were doing the SVD, I guess like, did you find any like top principal components that are actually more useful or anything like that?
So these are sorted in terms of explained variance.
Oh, I see.
So actually, you can think of like an alternative way to think about SVD on the adjacency matrix is it's also just PCA.
Exactly.
On
That's
the data model matrix itself. And then that is a sort of even nicer interpretation because you can think of the explained variance in terms of like how much of the prediction does it explain. And so these are sorted by their explained variance.
And just so approximately, so if you have like a 50,000 training set size, what portion of like how many principal components did you actually see?
That's a great question. I hope that I have an extra slide that does this, but I'm not.
Oh, okay.
Okay, no, I do not. But in the paper we have, give me 1 second actually, because it's actually quite high dimensional is the point that I wanted to get across. Is it okay if I share a screen other than?
Oh yeah,
Keynote?
Go for it.
Okay, new share. I will try to do this properly. Okay. Do you still see Keynote or did it switch?
We still see Keynote. I think maybe it's sharing Keynote specifically instead of your screen. So, okay, now we see your.
Okay, cool. I realize this probably wasn't the fastest way to load the paper, but that's okay. Okay, so if we look at so this here is a plot of like the number of components and the amount of variance explained.
Okay.
And so the blue line is like if you use a representation space that comes from like the second last layer of the model. And so there, as you might sort of expect, like you basically only need 10 principal components to explain the variance, which sort of lines up with like the number of classes. Like you don't actually care about, like there's no real reason for it to have more than 10 dimensions. And the data model space looks like this orange line here. So like even if you use 500 components, you still only explain about half the variance.
Interesting. So does this mean that, is that basically why we are able to see more subpopulations via data models? Is that an interpretation?
That is an interpretation, and I think this is going to be in an appendix, and so we'll see how fast I can find it. I won't spend too much time on it. Okay. Okay, yeah. So I guess you can sort of see like for representations, once you get past, so these are the top 3 principal components for neural network representation space. So there's 2 sort of interesting takeaways here. One is that you don't see this like opposing feature effect that we were talking about earlier, because there's no, and this isn't like a causally relevant space. Like there's no reason for these to be opposing. They're just different. The other thing is once you get outside of the top 10 principal components, like if you go to principal component 43, things start getting a bit random. Like you get like a mix of like cats and deer and dogs, and like there's no real cohesive thing that's happening here at all. So this is what happens if you use representation space. If we look at the same thing for data model space, we can go as far as like, this is like 56, this is 66, and these are just like random numbers. And the representations are still like super consistently a feature. So 56 was random, and 66 we picked specifically because it has LeBron James on a banana boat. But like you can see that the features are still relevant even as you get way past the 10th principal component.
Oh, that's pretty cool. Yeah. Nice. Great. So any other last questions? I guess we have a couple of minutes, but okay, then if there are no more questions, let's thank Andrew again. We'll have the YouTube video up later tonight, and then we'll share it with all of you. And if you have more questions, you can always feel free to get in touch with Andrew, or you can reach out to us and we'll be happy to connect you as well. But yeah, see you guys next week. Have a good weekend.